So in our example here, cystic fibrosis and Huntington's, you can see their, um, well, at least Huntington's disease is caused by this dominant allele, and that's different from a lot of the other, like hemophilia and cystic fibrosis. So, for example, if you have one parent with Huntington's disease here, you can see 2 out of the 4 kids are going to get it. And Huntington is something that comes on, late in life, usually in the 60s or 70s, late in life. So it's not something you see. It definitely can't get taken out of the gene pool because it affects people way after, the kids. And here's cystic fibrosis. You can see you got to have the recessive alleles in order to get it. So see, both of this is a situation. Both of these parents are carriers, and then 1/4 of their kids will have it. And this typically affects people with certain ancestry. Ashkenazi Jews, for example, are more likely to have this. So people know they have that in their background. They might get tested for this beforehand. Like my wife is Ashkenazi Jew, but I'm not. So pretty unlikely that our kids would have it. So we didn't get tested. If you have kids one day, and you go get your prenatal care, they'll offer to test, you and your partner for lots, maybe 300-400 diseases. But it's everybody has some disease tendency. You really can't predict things like that. Try to map out your life, based on a genetic test. It's pretty difficult. So I'm not sure. You've definitely heard of Hiroshima, but I don't know how many of you have heard of Chernobyl. But there's a nice little write-up in this in your book, page 184 to 185. So Hiroshima and Nagasaki, of course, in 1945, near the end of World War II, where these hydrogen and plutonium bombs were dropped over these Japanese cities. I think it was 2 or 3 days apart, and killed hundreds of thousands of people initially. Yeah, you saw here 250,000 people died from the bomb, but also the big fear was cancer showing up later. And when this happens, you have these cancers early on. Usually you get a lot of stillbirths, but very interestingly, there wasn't a lot of evidence to say we had stillbirths, or there were stillbirths based, from that explosion. And it's also difficult cancers. People usually get cancers 50s, 60s, 70s. It was very difficult. Sometimes you can tie certain cancers, certain exposures people have, say, unnaturally high number of people are suffering from, say, thyroid cancer that works in a certain area, around Nagasaki or Hiroshima. But they saw the people who were getting thyroid cancer were spread out around the country that weren't necessarily exposed to that radiation. So it was really tough to really demonstrate scientifically there was a link there. However, the people that were exposed to that suffered a lifelong stigma, has stigma attached to them. It was difficult for them to, say, find a wife or a husband because they were thought to be damaged from, being exposed to that radiation. So probably socially more than physically, the damage was done to the people, or medically, that social damage. Kind of like, we have diseases and there's a lot of stigma attached to them. The one that pops in my mind right now, HIV, or other sorts of diseases. People like lung cancer, people say you deserved it because you smoke, and a lot of people never smoked at all. Cancer. This is Nagasaki, and this actually was the structure. It was located a couple hundred feet below the bomb, below where the bomb exploded. Bombs do much more damage if they explode before they hit the ground. So usually they're timed to go off when they're, say, 500, 600 feet above the ground, and then they cause a lot more destruction. And this structure was directly under the blast and was spared, did not get completely destroyed. And then Chernobyl, this happened in 1986 in my lifetime. And I actually lived close to a nuclear power plant up in Yakima, Washington that was called Hanford. It had the same basic design that the one in Chernobyl had. So people were a little concerned around Yakima when this happened. Anyway, there was a runaway fission reaction. Normally, these are cooled down. There's systems that'll keep that reactor core from getting too hot, but they failed. The pumps were, I think they were deactivated, and there was some confusion among the operators what to do. And the heat built up and it exploded out of the core, and there wasn't any containment. Normally, you have the core and some big containment structure, but there wasn't anything like that. It was just a regular building. So boom, the radiation went everywhere and then flew over Europe. If say, oh man, Europe is hard to draw even for me on a good day. Here's Europe, England, France, Italy, and then here's Russia and Asia, Chernobyl here. That radiation kind of spread northwest over not the Balkan, but Belarus, Poland, Latvia, Lithuania, Norway, Finland, really kind of went into the Baltic Sea here. And so this area of northwest Europe really got, or northeast Europe really got hit hard. I think it was 4 kilometer square area of forest around the nuclear plant died, and horses and cattle nearby. And then here, unlike in Hiroshima, they did link some thyroid cancer to people in Chernobyl. The interesting thing is, since Chernobyl was a no-go zone from ever since 1986, and there weren't people living around that area, it became a great wildlife sanctuary where a lot of animals could live out their lives without being affected by humans. So ecologically, it ended up being a positive thing, and really helped aid forest animals in that area, like foxes, wolves, deer, other sorts of animals thrived. And this is the building. If you think about a nuclear power plant, a lot of them are built with this big containment structure. It kind of has this kind of hourglass shape, and you'll see steam coming off. And this is all built to contain the core, so this doesn't happen. This is just a regular building. It exploded, boom, went everywhere. And there were a lot of really brave individuals that went in to basically construct a sarcophagus over this. It's called a big structure, just to quickly build it and just to seal it up. And those people that worked on that did die from exposure. So here is this genetic cross. We gotta know. We have these true breeding parents. Homozygous dominant, recessive. When they mate, you'll see all the offspring have, this is the P generation, F1, they all have, they're heterozygous. Then the F2 generation that we see here, we have this, which is a 3-to-1 phenotypic ratio, right? Oh no, this is wrong. 2 little t's. 3 of these are tall and 1 are short, so 3-to-1, but the genotypic ratio is 1:2-to-1, which is behind my face right here, I think. So we did an example of this. So this is something you should be able to do. P generation, F1, F2, hybrids in that F1, and then resulting in that 3-to-1 ratio, and that 1:1 ratio. Those ratios are something that you definitely to know. So let's do these real fast. This is for color blindness. Okay, this B is a colorblind gene. XX. Ivan's playing. Ivan, how's that Fortnite going? Good, all right. V-Bucks, what a scam. So you should have something like this. Maybe you pause the video before you watch me do it. So the genotypic ratio, the genotypes. So these are two different genotypes for the X's. So we have a carrier and totally normal, and here we have a male with color blindness, and then normal. So this is a 1:1:1:1 genotype ratio. And phenotype ratio would be colorblind, not colorblind. And in this case, we have 3 not colorblind, 1 colorblind. And here, you remember what this is? This is not Huntington's. Hemophilia from, one of my favorite activities, the Romanovs. So, poorly written, but here we have our X's. I gotta fill in regular H's. I don't have those. I don't know why, but this is a carrier female. This is a normal male. This is a carrier female. This is a normal male. So it's kind of interesting. The father has hemophilia, but his sons don't get it because his sons all got the Y, which doesn't have anything to do with hemophilia. But all of his daughters got his X, so they're all going to be at least carriers. And the mother's normal, we'll say, I just wrote in there. So they don't have hemophilia, but they can, of course, pass it on. So the genotypic ratio, we have 2 that are carriers, and then we have 2 normal males. So it's a 1:1 ratio. We'll reduce it. I'm sorry. Yeah, those are exactly the same. And the phenotype ratio is just, we have half that are carriers and half that are just normal. So 1:1. 2 carriers here, 2 normal males. Definitely make sure you understand the difference between the genotype and phenotype. So this Nature of Science article, 169 and 170, we went over in class for a warm-up, and remember we predicted that 3:1 ratio based on the Punnett square that we just did earlier, but the actual outcomes were a little bit off. We're not quite 3:1, but very close. So in this case, the predicted and actual, they matched closely, which is what we would expect. That's this is to be expected due to random chance. Sorry for the handwriting. Seem to be on an off day, but like I explained this. Think about families, that have maybe 5 boys and 1 girl, or vice versa. You're like, that's kind of weird, right? Because every time a couple has a child, it's 50%. So why does that happen? Just random chance. If they ended up having 50 kids, it'd probably be more equal, but most people don't. So if they just have 3, 4 kids, they might all be girls, might all be boys, and that's not that unexpected. If we see exactly 3:1, that might be suspicious because the actual outcomes are usually not quite. So when you look at pedigrees, there's some tricks you need to keep in mind, and the main ones for recessive traits is that they skip generations. So you might not see the parents have it, but it'll pop up in the offspring. That's definitely a recessive trait. So that means dominant traits do not skip generations. If you see it, if you've seen in offspring, 1 or more, one or more parents have it. Have the trait. Okay, it can't hide out and pop back up again. So it's the skipping and non-skipping. And for sex-linked traits, we see more males with the disease or the trait. I should say trait. That sounds bad. Trait is a better word than disease. So is this dominant or recessive? What would be your analysis? If you look, see how these parents, both had a child, married another man, didn't have the disease, but boom, it pops up in that generation. And here also, this offspring, nothing up here, but boom, pops up here. And it's totally fine in recessive disease for a parent who has it not to have any offspring that have it, like we saw in cystic fibrosis. So this would be recessive. And you'll see it's equal. We have 50% male, 50% female that have it. And for this one, we see something similar. Look at this. These parents don't have it. The kids, though, have it. So that's recessive. Okay? And if we label this, we would, anybody that has it would have the little a. Little a. And here, if these two parents have offspring that have it, they have to be heterozygous. So this one here could be heterozygous dominant or heterozygous. Here, if they have kids that have it, they're going to have to be heterozygous. And here, we know that, they would have to be heterozygous, because if they were homozygous dominant, all their kids would always get a big A. So we can definitely label like that. Here we see any child that has it has a parent that has it. You see in this line here, nobody has it. But here, whoever has it here has a parent that had it, had a parent. So this is dominant. Okay, that's definitely a dominant trait. So anybody who doesn't have it would be little a. So the easiest for to go and label everybody like that. And remember, just because something is recessive doesn't mean fewer people have it, and if just something is dominant doesn't mean more people have it. So this person would have to be heterozygous, otherwise all their kids would have the whatever that trait is. Not saying what it is. Not doing anything right now. Yeah, and they would have to be big A, little a. Okay, and you see an equal number of males and females having it. Sorry this video is so long, people. I get through it. So I want you to make one for your own family. Here's some cool symbols you can use. Divorces. A lot of people end up having, say their dad, and they'll have all sorts of lines. If he was the one that got divorced and remarried, he'll have kids coming out. But yeah, it can be really tricky. And everybody's family is unique like that. Here we got stillbirth, pregnancy. If somebody's pregnant, you can put in this circle with a P, or if you don't know the sex, this little triangle there. Here we got non-identical twins, identical twins. Cool. You can see this is for my family. You can see this is me, my wife, Simon and Ivan, my younger twin sisters, but not identical. My older sister has a girl, and my younger sister has a a 2-year-old, almost 2-year-old here. Simon, 13, almost 14, Ivan, 11. And here are my parents and my aunts and uncles up here. So go ahead and fill that in for your and answer these questions. Hemophilia, the genotypes of the parents, and carrier mother, normal father. The possible genotypes for the boys would be X big HY, X little hy. So this one's going to have hemophilia. And the girls, oops, sorry, I should have gone there. This is going to be regular, and this is going to be carrier, so 50% carriers. The phenotypes of girls and boys. For the girls, half normal, 1/2 carrier. And for the boys, 1/2 have hemophilia and 1/2 normal. So that's hemophilia, that's normal. Who are the carriers? It's this female right there. Wouldn't put him because males can't be carriers for a sex-linked disease. They either have it or they don't. So just point right there. And what are the chances that the parent's next child will have hemophilia? I think that's the question. It's always 25%. If it asks you what chances the parent's next male child, it would be 50% because half of the males have it.